Well, good afternoon, everybody, and welcome to the third and final webinar today from Smart Vision Europe. We're going to finish up looking at basic regression techniques in SPSS statistics. My name's Charlotte Quinn. I'm an analyst with Smart Vision Europe. If you haven't joined in these sessions before, and I know many of you have, might be worth pointing out these sessions are recorded, so you'll be able to listen to them again. And there is a bit of slideware at the start. There's a lot of demonstration, a live demonstration of working with the software, but a little bit of slideware to help put a bit of context around things, and we will email a link out to you so you can download the materials after the session is ended. If you think the session is particularly useful for colleagues who are unable to attend today and you get enough of them together, it may be possible for us to rerun the session. The best thing to do is just to ask us, drop us an email or something like that. With regard to asking questions, all the lines are muted, so we ask you to use the chat panel. And if we run out of time, and we do try to cram everything in here, we will follow up with you offline afterwards. By the way, you can also drop us an email if a question occurs to you afterwards. We're happy to answer those. I'll try and remember to check the chat panel before the session ends and address those questions. If you don't know who Smart Vision are, we are a technology organization. We're a gold accredited partner to IBM, as well as a company called Predictive Solutions and Data Robot. And we specialize in statistics, advanced analytics, machine learning, data science, all that type of stuff. Especially focused around the SPSS product line, the brand name of SPSS, which is of course owned by IBM now. And we provide that software and support and services around that. Though we do work with open source technologies like R and Python. And we are a relatively small organization made up of a veteran group of people who've been working in the advanced and predictive analytics industry, particularly the software industry, for decades. I think I first started working for SPSS in 1995, and I'd been already using the software for about 5 years prior to that. So we're pretty steeped in it. And that means that we've applied this type of technology and certainly these types of techniques that we're going to be talking about today across many different sectors, commercial and not-for-profit, for many, many years. And certainly what we're talking about today pretty much plays in every single sector I could think of. There's probably an application in whether it be healthcare or retail or central government or media or manufacturing for regression and for regression techniques. So our agenda today is to provide an overview of regression techniques and linear relationships, how to show you how to perform simple linear regression, take you into multiple linear regression that allows you to make predictions, and finish up looking at a completely different type of regressive approach, which is logistic regression. So it is a kind of a gentle introduction to regression. There's a lot more to it than this. I need to add to that. There's a lot of stuff we're not going to be talking about diagnostics and assumptions of regression and stuff like that. But certainly it'll give you enough to get you started and give you a sense of how to make sense of regression, if you like, and certainly how to interpret the output that SPSS produces. So the first thing is the term regression. So regression is actually, people say I used regression. They could be, they're normally, when they say that, they normally mean linear regression. That's kind of the grandfather of predictive modeling techniques. It's certainly the standard form of regression. But regression itself refers to a family of approaches, a whole family of approaches, of which we've only mentioned a few here. Linear regression is commonly used when the outcome is a number, a continuous, a scale variable, where the relationship between the fields can be described using straight lines. So it's linear in nature as opposed to non-linear. Quadratic is a variant of that, where the outcome is continuous, but the relationship is kind of curvy linear, so a bendy relationship, which you might get, for example, I don't know, between something like engine size and fuel consumption or something like that. You find that it's not necessarily a straight line relationship. A logistic regression is probably the second most commonly used form of regression after linear, and that's used when you have a category outcome, two or more categories. When it's two categories, it's called binary logistic regression. When it's more than two categories, like three different groups that you're trying to predict on, and that's called polynomial logistic regression. And something which I'm working on currently, Poisson regression, we're doing a video on that. That's also used when you're working with continuous data, but it's where the data with a dependent variable, it actually records counts of events. So it tends to work with situations where people have a lot of zeros in the data, where the event didn't occur, and where the event doesn't normally occur more than, I don't know, 4 or 5 or 6 or 7 times or something like that. So it'd be things like Poisson regression could be used again in modeling things like, the number of goals scored in a football match or something like that, or the number of times that somebody relapses in a treatment program, or the number of failures that a machine or an asset exhibits over a 2 year period or something like that. So there is a family of techniques. Regression techniques are used when we're modeling the relationship, for example, between things like promotion and spend. I'm trying to think about linear regression here. I should really say where linear regression techniques are used. So promotion, spend, how much you spend on advertising and how much you spend on revenue. It does make sense that the bigger the advertising budget you have, the more revenue you get. But there's a point whereby it obviously doesn't pay to do that, and it becomes counterproductive. But things that I've done are things like estimating pollution levels following heavy rainfall for the Department of the Environment. You can use a regression to estimate the amount of pollution in the sea and in coastal areas following a period of heavy rainfall, because a lot of pollutants get washed down off the fields and get discharged from sewer pipes and stuff like that into the watercourse. Or predicting tourism revenue based on things like exchange rates and air travel costs, because air travel and exchange rates definitely affect the number of visitors you're going to get to, let's say, a Mediterranean island or something like that. Predicting test student scores based on that student's previous results and perhaps how their class is performing historically. Estimating the number of website hits, number of visits to a website based on things like social media promotion, TikTok videos, or retweets and follower numbers, the level of influence that an influencer has, or things like using meteorological data to predict sales of products which are sensitive to that. So predicting things like sales of barbecues based on temperature forecasts. These would all be, there are a very wide-ranging array of different applications there, but you could certainly imagine using linear regression in all of those situations. So the term regression may not be obvious, actually comes from the term regression to the mean, meaning falling back to the mean. It refers, I think it was Francis Galton who originally came up with this, who's a historical statistician, one of the fathers of statistics, who was trying to predict things like the heights of children based on their parents' heights, and noticed that you couldn't perfectly predict the height of, let's say, a person when they come to adulthood based on the height of their mother and the height of their father. Um, the two were related, obviously, but they didn't perfectly predict it. And he noticed that there was almost a tendency for people's heights to kind of fall back towards an average, if you like, so the average value. And he called that regressing to a mediocre value, meaning regressing, falling back towards the mean. In regression, the mean is very important. The average is very important here because the average can be represented by a straight line, and that straight line we're going to come on to in a moment. But suffice to say that when we visualize regression, we tend to use scatter plots like the one you're seeing at the moment, where we're looking at the percentage of unemployed in different US counties and the percentage of people in those counties that are reliant on public health care. Okay, so the more unemployment you have, generally speaking, historically, the greater the reliance on people using public health care as opposed to private health care, which of course is very important in the US. Now, regression to the mean refers to this line that you can draw through this scatter plot. This line represents a kind of average. It's kind of the average of the relationship, if you like. If you were to look at the relationship between percent of the average relationship between percent on public healthcare and percent unemployed. And the line, if you were to draw it manually, which you wouldn't do because you can calculate it, but the line is drawn in such a way that it minimizes the difference between the average, the line itself, and the points itself. And that's why it's called the line of least squares. So you'll often hear classic linear regression referred to as OLS, meaning ordinary least squares regression, because the purpose of the line, when the line itself is kind of the model, is to try to minimize the square of the differences between the values. Why the square? Simply because some of the differences are going to be minuses, because they're going to be below the average, and some are going to be above the average. And if you added up all the positives and all the minuses, you just get zero. So statisticians don't like that. So they tend to square the difference. So a difference of 2 would be squared to 4, and the difference of -3 would be squared to obviously to 3 to 9, sorry. And if you total up all those numbers, the smaller that number is, the argument being the better the line fits, or the better the points actually fit along the line. So it's the line of least squares. Now the thing you have to bear in mind is this line is just a kind of average. So you can get exactly the same line even when the data looks completely different, So you can see here in this first example, this is from a famous set of drawings called Anscombe's quartet. This first example shows a relationship between variable x and variable y, and it looks like a kind of classic scatter plot, looks fairly reasonable drawing of a line. The second one is a curvy linear relationship. The line doesn't follow curvy linear relationships, so it doesn't really fit what's happening. It just comes out as a sort of brutal diagonal line. This one down here, this the one down in the bottom left, actually shows that the line can be affected by extreme points. If that point didn't exist, that average line wouldn't look like that. It wouldn't be as steep as that. It would be a little bit shallower. So extreme points can drag the line up because the line isn't average, in exactly the same way that if you're measuring the heights of people and somebody walked into a room who was 9 feet tall or something like that, the average height would go up. And this is true even when you only have 2 data points. Here we have a data point. We've got a bunch of data points where they're all equal to the value 8 in the bottom right-hand corner. And we've got one data point here where it's equal to the value 20 or 19 or something like that. It still can draw a line between that. So the point is I guess it's a good idea to visualize your data beforehand and get an idea of how the variables and how the fields are related to each other in linear regression using things like scatter plots, and we'll certainly be doing that. Now, if we were to measure these relationships in scatter plots, that we're saying these relationships between these scale variables, these continuous variables, we normally use something called a correlation value. And in fact, we have a webinar devoted entirely to correlation and understanding how correlation values are estimated and how they're predicted and sorry, how they're calculated and how they can be used in different ways, and how there are different types of correlation for rating scales as there is for individual values. But Pearson correlation values are kind of the classic way to represent the strength of a linear relationship in a scatter plot. So here we have 3 scatter plots, and each of the points within the scatter plots refers to automobiles, refers to cars. And we've recorded their vehicle weight here, and we've recorded the horsepower, and we're getting a correlation value here of 0.859. Well, what does that mean? Well, correlation values run between 2 extreme points, and they can't exceed those extreme points, -1 to +1, with 0 in the middle. And the closer it is to +1, the stronger the positive relationship is, and the closer it is to -1, the stronger the negative relationship is between the two factors. It doesn't mean that one factor is dependent on the other. It doesn't make really any difference whether or not you flip the axes around. The correlation is not affected by that. And we can see here that horsepower and vehicle weight give us a score quite close to 1 of 0.859. So that's a really strong, as we can imagine, it is trying to form a line here. So you can imagine it's quite a strong linear relationship. Whereas the time to accelerate from 0 to 60 and miles per gallon, which is also linear, is also a sort of linear relationship, not as strong, has a score of 0.434, closer to 0, if you like. So it's a weaker relationship. In other words, horsepower is a really good predictor of vehicle weight, and vehicle weight's a very good predictor of horsepower. Miles per gallon is a not so good predictor of time to accelerate, and time to accelerate is not so good a predictor of miles per gallon. And then we have a negative relationship when we look at horsepower against time to accelerate. And it's basically saying, look, if you've got a car that's got really good horsepower, it doesn't take you very long to accelerate from 0 to 60. Whereas if you've got a car with very low horsepower, it takes you longer. It's a negative relationship. As one value increases, the other value decreases. It would be exactly the same if you're looking at things like the relationship between blood alcohol level and reflex reaction time. So these are, these certainly the ones on the extremes here, the two charts on the far side of the slide here. These are quite strongish, quite strong correlations, I would say. This is a kind of a weaker one. In social sciences, I would say if you get below 0.3, it's really, they're quite weak relationships. A correlation of 0.2 might be statistically significant, but it doesn't mean it's a very strong relationship. If we were to continue this situation and look at something where there isn't any relationship, really, we might look at mileage, which is the mileage of the car, how many miles are on the clock, and miles per gallon. And those two things aren't related to each other in any way, and we wouldn't expect them to be, because that's really the age of the vehicle versus the fuel efficiency. And thus we get this random cloud of points. The value is quite close to zero. There's no real strong linear relationship there. And here we can get strongish negative relationships, minus 0.67, or strongish positive relationships, even if, as we've seen with Anscombe's quartet, even if the relationship is not linear in nature. This is kind of a hook-shaped relationship. This value here relates to how well these points fit this straight line, which is not that great, but or certainly not for this part of the scale. Maybe a bit better this part of the scale. So the lesson here is make sure that you visualize your data beforehand. Sometimes statisticians might do something to a variable to make it linear. You can see here that this is miles per gallon squared. So I squared it to create this relationship. And as a result of that, sometimes people take the square root of a variable or take the log of a variable in these situations to crunch the numbers back down so that you get a linear relationship between the two fields so that you can use them in techniques like linear regression. Okay, why are correlations related to linear regression? Well, correlations tell you how strongly related along a bounded scale two variables are. So going from -1 to +1, closer they are to those extremes, the stronger the relationship. Closer they are to the center, 0, the weaker the relationship. Well, it turns out in regression, we use a value called the R-square, and it is literally the square of the correlation. If you think about it, you take a correlation here of 0.859. If I square that and multiply it by itself, I get 0.738. And that can be interpreted in percentage terms. It means that 73.8% of the variation in one field can be predicted by the other field. It's the best way to think of this is to think of both fields as circles, and the overlap in the variance, the shared variation between them, the overlap is equal to 73%. So they overlap by 73%. And we'll return to that concept when you see us actually running correlations themselves. Which leads us to correlations as linear relationships as predictive models. How do we get there? Well, perhaps the easiest way to think of that is to think about that straight line that represents the average of the relationships between the two factors. And that straight line can be expressed in various ways, but the formulas pretty much add up the same thing. Like sometimes you'll see different formulas, and the way in which the shorthand way to kind of explain this is think about is how long it takes to cook a chicken. And the reason why we use this as an example is because if you go into a cookery book, for example, Julia Child's cookery book or Delia Smith's cookery book, they'll often give you a little formula that tells you how long it takes to cook a chicken. Julia Child's uses 7 minutes per pound plus 45 minutes. And Delia uses 20 minutes per pound plus 20 minutes. So they're very different formula. They might be set at different temperatures for the oven. So these formulas are used against standard conditions that the chicken hasn't been taken straight from the fridge. It's been sitting for a while. It's You know, it's no cooler than 5 degrees Celsius or something like that. It's not a fan assisted oven and you haven't basted it. Under standard conditions, this is how long it should take to cook a chicken. But the point is that these formulae can be expressed mathematically. And depending on whether or not you're a statistician or an economist or a mathematician, you might see a formula like y equals mx plus c, or y equals a plus bx, or y equals bx plus a. It's the same formula. It's just using different letters in a different order. It's the same formula. And the key here is that they have a constant on the end. That's the plus 45 minutes or the plus 20 minutes. So that's the a here or the c here. And it's saying that, no matter how much the chicken weighs, you got to cook it for at least 45 minutes. Or in Julia Child's world and in Delia's world, no matter how much the chicken weighs, you got to cook it for 20 minutes. So if you've got a 5 pound chicken, it's 5 times 20, it's 100 minutes plus 20 minutes. It's going to be about 2 hours or something like that to cook the chicken. And it's a prediction, isn't it? It's literally a predictive formula. Well, this is a regression formula. This is a linear regression formula that just happens to be the formula for a straight line, which we were taught in school, I'm sure, for most of us many years ago. And that is the basis of linear regression. Linear regression gives us these elements. It gives us these two crucial numbers, the 7 minutes per, the minutes per pound, plus the constant. And those are the two key elements. We're going to see those elements when we run our own linear regression. So when we do a linear regression, when we do a scatter plot in SPSS and we ask it to put a fit line through it, it tends to give you this formula at the same time. Here you can see the constant, that's 10.13, and the coefficient, which is the per, 1.16 per x. What's x? Percent employed. So if you wanted to predict percent reliant on healthcare and you had 10% employed, it would be 10%, 10.13% plus 10% multiplied by 1.16. So it would be, 11.6%. So it would come to, but something like 22% or something like that. That would be your prediction. So it's going to give you this formula, and then we're going to see this when we actually look at linear regression within the SPSS statistics. So let's do that. Let's jump out and have a look at a data set here. Here's our data set. This is a data set I've been using all day. This is the employee data set, and we've got some nice data to work with here because it's very easy to understand. Each row represents a different employee within a bank, and we have information about their current salary and information about their starting salary. These two columns here, beginning salary and current salary. If we wanted to establish the correlation, the Pearson's correlation value between these two, we would simply go to Analyze and down to Correlate, Bivariate, and we do a correlation of current salary against beginning salary. And I would normally say, show me only the lower triangle of the matrix and don't show me the diagonal values. It just means to get an easier to interpret piece of output. I think most people prefer this way of showing it. And here it tells me that the Pearson correlation value is quite strong, 0.880. So it's quite close to 1. It's 88%. It's quite close to 1. It is statistically significant, as we would expect. The significance test here is actually testing the null hypothesis that the correlation is in fact 0. Well, it's unlikely of 474 cases and a correlation of 0.88 that's just a random fluke, and that in reality in the population of bank workers out there that there's no relationship between beginning salary and current salary. The correlation is 0. So of course it's statistically significant. And if we were to square that, we'd get about 77%. It would mean that if a current salary has a 70% overlap in terms of its variation with beginning salary. In other words, we could estimate with a 77% accuracy on average some of these current salary if we knew the beginning salary and we had the regression formula to help us do that. Now, if you think about it, correlations are a good way for us to kind of a good way for us to quantify the relationships between variables. And we could if we took a correlation of 0.4 and we squared that, would be 16. It would be 0.16. That would be equivalent to 16%. 16% overlap. If it's a correlation of 0.5, you square that, it'll be 0.25, of course, 25%. 0.6, square that, 0.36, 36%. You basically got to get to a correlation of 0.7 where the two circles, the Venn diagram overlaps and half of one circle's in the other circle. So you're getting up to, because 0.7, of course, squared would be 0.49, or just under 50%. In this case, it comes out, if this was 0.9, it would be 81%. We'd get what we call an R square of 81%. But it's just below that, so it comes out about 77%. And we can see that because if we go to analyze and say, I want to actually try and find out what the formula is that predicts people's current salary based upon their beginning salary, we'd go to analyze, go down to regression. You can see that, we'll talk about this later, but there's a lot of different regressive techniques. I did say it's a family of techniques out there. Some of them are very, very esoteric. And the one that we would normally use is the linear model here, the linear regression. And our dependent variable is the thing that we're trying to predict, the thing that we're trying to model. So we're trying to predict people's current salary. And our independent variable, this is called a simple linear regression because we're just using one field against another field. It becomes multiple linear regression when we use more than one field against the target field. So you've got multiple independent fields or predictor fields. Sometimes it's called the target. Sometimes these are called the predictors or the inputs if you're working in the machine learning. But here they're called dependent and independent. It doesn't really mean that one is dependent on the other, but traditionally that's what the relationship is. And if I click OK at that point, it's going to produce some regression output for me. So here's I'm just going to hide the correlation. Here's my regression output. What's interesting is that certainly within statistical packages like S plus or Stata or SPSS or SAS, when you run a regression procedure, like a linear regression procedure, you do tend to get very similar output from one to the next. They tend to be organized in a particular way, and there's a kind of a convention around that. The first thing that we see here is it's just telling us that we've used a method called enter. That means forced entry. That means we're forcing the variable beginning salary in there, whether it helps or not. And then it gives us a model summary. And the first thing we see is an R value of 0.88. Where have we seen that before? We've seen it here. It's this number. It's the correlation. And the square of that, we square that, we get 0.775, 77.5%. And then there's another value here called the adjusted R square, because it's the square of R. It's a little bit below. This is the value which people normally quote when they're talking about how strong the linear regression was in terms of predicting the outcome, the accuracy of it. They'll say the R square was, the adjusted R square was 0.6, or it was 0.5, or it was 0.7 or 0.8, something like that. And adjusted is simply adjusted to take account of things like the variation in the data and the number of cases that you have. If you don't have a lot of cases and a lot of variation in the data, you may see that there's quite a big difference between the R square and the adjusted R square. So the adjusted R square just tries to take into consideration the amount of data that you have and the variance. It's based on this standard error. The standard error here is telling us how much the mean value is likely to vary from one sample to the next. It's like a standard deviation, but it's showing us how much it's likely to vary from one sample to the next. The smaller the standard error, the more reliable the data set, and you'd get a really small standard error of the estimate if you have a really large data set and not a lot of variation. But here it's not typically something that people would quote very much, but it gives you a rough indication of how reliable the data is, plus or minus $8,000. And the next thing we get to is an ANOVA table, analysis of variance table. This ANOVA table is sometimes referred to as an omnibus test. This is just a test, an overall test of whether or not the model is doing anything better than random. That's basically all it's doing. So we pretty much always expect it to be statistically significant, less than 0.05. Here it's less than 0.001. So it's definitely statistically significant by the use of that term. And it's comparing how well beginning salary does at estimating people's current salary compared to, say, just taking the average, just taking the average or just using what we call the intercepts, the minimum value. So, of course, it's better than just taking an average. We've seen from the scatter plot that it's better than just taking an average, and it is statistically significant. You still get a statistically significant result even when the R square is, really quite weak, down to like 0.2 or 0.15 or something like that, because it still means you're hitting quite a low bar there, trying to do better than just comparing the average. And then we get our coefficients table. And this is the bit where everything happens. This is the 20 minutes per pound plus 20 minutes per good measure. This is our y equals mx plus c, or y equals ax plus b, or whatever way you want to express the formula for the straight line. We have our constant. That's the plus 20 minutes per good measures. It says no matter how much somebody is currently earning, we're going to assume they earn at least $1,928. So that literally refers to the dollars. And this is the per bit. So we're saying for every unit of beginning salary, you multiply it by $1.9. So if their beginning salary was $10,000, we're going to assume that they're currently on $19,000 plus about $1,900 on top of that. So just a bit over $2,100. It was what we'd predict them to be on. And we have standard errors telling us how reliable these statistics are. We have something called a beta value here, which you'll see is exactly the same as the R value, which of course was exactly the same as the correlation. And that value will always be the same as the correlation when you're only using one variable to predict the outcome of another variable. In other words, when you're only doing a simple linear regression. Furthermore, it tells us whether or not these are called the terms in the equation, the a and the bx, or the plus c and the coefficient and the constant. It tells us whether or not they're actually statistically significant. We see the constant here is statistically significant, less than 0.05, and the beginning salary is also statistically significant. And that is our formula. We could take this formula. We could then apply it like in Excel or something like that. We don't have to do that in SPSS. It'll calculate it for you. But it would then estimate what people's current salary was. Now, what's interesting is what happens when we change things. So let's see if I change this and I say, okay, look, let's not use beginning salary to predict current salary. Let's use education level. Okay, let's use years education. What happens now? Well, it turns out it's a weaker model. We're using a simple linear regression. The correlation here is 0.66, which means your adjusted R square goes down to 43.5% or 0.435. It's not as strong. It's still, of course, statistically significant. You can see the beta value here is 0.66, and the formula is different. Now the constant is a minus number. It's saying, okay, for every year of education they get, they're going to get $3,909 in their current salary. And then you're going to take off just under $2,000 at the end of that. So sometimes the constant is actually a minus number, which means that the line crosses the negative part of the vertical axis, the negative part of the y-axis. But the coefficient here, the what's called the standardized coefficient here, beta, is equal to 0.661. It's the same as the R value, which means it's the same as the correlation between education level and people's current salary. So what happens if we put both of them in? If we put both of them in, would we get the same coefficients? Well, clearly not, because the constants changed. And what about these numbers over here? Would we get the same beta values as the correlations? Well, no, you won't get the same. We'll explain why. Let's put beginning salary back in. So now we've got two. Now we're doing multiple linear regression. It doesn't make any difference what order I put them in here, because I'm using the enter method and I'm forcing them in together, irrespective of whether or not they help. I click OK at this point. Now the R square has jumped to 0.792. Previously, the best we did was 0.774. So it's gone up a little bit, about 2%. And it's gone to 0.792, just under 80%. The standard error estimate's got a little bit less. Of course, it's still statistically significant. The R value here is 0.89. That's kind of the combined correlation, if you like, of the two variables against the target variable. And now we have a different formula. Now we have beginning salary is equal to 1.6. So for every dollar of beginning salary, you get $1.67 of your current salary. And for every year of education, you get $1,020. And then you take off your minus number at the end here. And what's happened over here is that these standardized coefficients have changed. And these are called partial correlations. And what they're trying to do is they're saying, I'm going to tell you what the correlation between beginning salary and current salary is in the presence when I already know somebody's education level. Assuming everybody's got the same education level, this is what the correlation is. Whereas education level is much weaker down here, it doesn't contribute as much. Previously, remember, it had a beta coefficient here of it had a value of 0.661. Now it's dropped to 0.172. Well, they're competing to predict the same thing. So it's a bit like me trying to predict how long it takes to cook the chicken and adding in the variable temperature. You know, time to cook the chicken. We're using weight and we're using temperature. But they've both got to reconcile with each other. And the reason why that's the case is because these two variables are not completely independent one another. They overlap with one another as well. And we can show that because if we do a bivariate correlation and we look at beginning salary against education level, we get a correlation of 0.633. So given the fact that they correlate with each other, and they're not truly independent of one another, they've got to, they've got to come to some sort of reconciliation when it comes to the predicting the outcome, and they're both not equally strongly related to the dependent variable. So the beta coefficient or the standardized coefficient here are slightly different. So these are really useful because it tells us what contribution each variable is making to the equation, to the model that we're trying to build. I should point out here that in this B and beta, this is just the same thing. This could say beta. I don't know why they use a different naming convention, but it's B and B really. And the difference here is that this is a standardized version of this. This is standardized them so that they've been turned into correlations rather than their raw numbers. That's the only difference. What happens if I add in more fields? If I add in more fields at this point, I could add in age. And I could add in, let's say, months since hire, how long they've been in the job. Now, again, sorry, that's the wrong one to use. I meant to using linear regression. Let's go age and months since hire. We're using the enter method here, remember? Click OK. Now the overall adjusted R-score has gone up to 0.81, 81%. And as we scroll down through, these all look like they're contributing positively to this. Is it worth it? Well, one of the ways in which we could see which ones are contributing individually, if you like, as we're going along, is to use a different method. We have a method here called forward and backward. There's another method called stepwise and remove. Think of forward as a bit like building a house of cards, where you're trying to build a stack of cards, put one card on top of the other, and try to keep doing that without the stack cards falling over. That's what forward's trying to do. It's trying to add in only variables that will statistically contribute towards it. Whereas backward is a bit like Jenga, where you add them all in and then take out the stuff which you don't need in order for the tower to still stay upright. So if I use the forward method here, I wouldn't normally recommend using the stepwise method. You hear people talk about that. There are problems with it. It looks like stepwise will actually add in a variable and then take out a variable if it's no longer significant. It gets a bit more complicated. It's not something that most people recommend doing. So forward's a little bit more conservative. Click OK at that point. And what it does is it doesn't just build one model, it builds 4 models as it's putting each one in at a time. And we can see the R-square going up. Okay. And as a result of that, we get 4 ANOVA tables saying model 1 had 1 variable, model 2 had 2 variables, model 3 had 3 variables, model 4 had 4 variables. And they're all statistically significant. They're independent models. And then we get down to the coefficient table here. And we can see the first one started out with beginning salary. The second one added in age. The third one added in months since hire. And the fourth one added as a 4th step, education level in years. And in fact, you can double click on this and you can call up what's called pivoting trays and put the model in here and drill down into each one of them at a time. You can see the coefficients changing. There was our simple linear regression. And then we added in model two. Look, it shows age as the next best predictor. That goes in as it's actually got a minus number. So it's saying the older you are, the less you earn. That's true in this data set because some of the oldest people are working custodial and clerical groups and they don't get paid as much as the younger managers. As we add in category 3 months since hire, and we can see that this is not strong correlated, but still statistically significant. And the last one is education level in years actually goes in last of all. It's a little bit stronger, but it's the formula now is equal to minus 12,512. And our formula is now no longer y equals mx plus c, but it's y equals beginning salary times 1.758, plus age times minus 160 dollars that you lose for every age in the year, plus months since hire, 169 for every month since hire, plus education level. Every year of education gets you $664. And then you take away $12,000 at the end, and that gives you your prediction. Now, at this point, things do start to get complicated. You'll see things like collinearity and things like that. What linear regression doesn't like is it doesn't like variables where there's a lot of strong correlations between them. It likes them to be really independent one another. And there's a lot of stuff I haven't talked about here where you'd have to test whether or not the model fits well, whether or not it meets certain conditions. There's a lot of emphasis upon the difference between the prediction and the actual value. That's called the error or the residual. And I can get SPSS to save out what's called the unstandardized predicted values and the and the unstandardized residuals, the error. Click OK at that point. It runs it and it actually gives us our predictions here. Let me just change these. I'm going to change these so that the decimals are removed so it makes it a wee bit easier and to see them. And I'm also going to change the type so that they're dollars. So it's easier to see that. Dollars. So here are our predictions. It says I predict this guy to be on $55,000. I was $1,869 below, because you can see the actual salary here was 57,000. Here I'm predicting $42,000. The error ticking the actual value away from the predicted value is it's under by $2,000. So it's actually they earned $2,000 less in this prediction. And one of the things that statisticians will do, they'll spend a lot of time analyzing these residuals and seeing if they get larger as the values get larger. That can cause a problem with the model. Notice that if I go down to the bottom here, I have got an extra case at the bottom here. And this extra case, we don't know what somebody's salary is. Their current salary is missing, but we've got all the other values. We've got their age, their education, we've got their beginning salary, and it still produces a prediction for us. Obviously, it can't produce a residual because it doesn't know what the original or what the true value is. And the point here is that you can get it to produce these predictions for you, and you can add on extra rows of data, and it will simply predict through them. An alternative approach to saving your model out, if I go save here, I'm just going to switch off the residuals, is you can export the model as a file. I've got the file. I've already done it here before. You can export the whole model as a file and call it an XML file. It's called called porting the model. Click continue at that point. I'm going to overwrite the old one. And then if I just go back to, I'm just going to delete these values here so it makes it nice and easy to understand. If I go back and then delete this field salary here completely, and imagine it's a brand new data set, I could go to utilities, go to scoring wizard and call up my regression webinar model that I just exported. It matches the fields. And I could say, okay, show me the predicted values. And it will score the data set with the predicted values again. And that's how we can save the model away and apply it to a new data set. Okay, listen, we've only got 15 minutes left. And we need to now, having established the basis of linear regression, move on to a completely different approach, which is logistic regression. And logistic regression is somewhat harder to get your head around, but it's a lot easier if you understand how linear regression works. So logistic regression does things that linear regression can't do. So logistic regression will help you predict things like whether or not somebody responds to a marketing campaign, or whether or not they're a good credit risk or a bad credit risk, or whether or not a subscriber is likely to renew a service, or the risk of a piece of equipment failing, or how likely it is a particular patient be readmitted to hospital, or whether a charity donor will switch from cash to direct debit. So these are category outcomes. And because these are not continuous numbers, linear regression doesn't work with them because it doesn't understand categories. So when the outcome consists of two categories, we use binary logistic. And when it consists of more than two categories, three or more categories, we use multinomial logistic. Logistic gets around the limitations of describing relationships with straight lines by using a special curve. Now, if you imagine here, I've got an iPhone 16 and I'm trying to sell a bunch of iPhone 16s. And I'm selling them at my standard price, which is, probably even more expensive than what Apple's selling them at. But I start to offer a discount until I get to 100% discount. Well, assuming I get 100% discount, all of them are going to get sold. So the probability of people buying them is going to be close to 100. And this special curve here describes this relationship that as a value increases, the probability of something increases as well. So it could be, the probability of somebody having an accident if they're drunk and what the blood alcohol level is high, or the probability of somebody responding to an offer of a really good discount effectively. So there is a special formula that converts the values on this x-axis here into these probability values by using this special curve here. And this special formula is called a link function. And that leads us to ask, well, what are these numbers on this x-axis that allow us to convert them into probabilities? Well, these numbers are the numbers or the values that logistic regression creates and puts through the special formula called the link function, which creates a probability. And what that means is that the coefficients in the logistic regression are not like the coefficients in linear regression. They're not going to be like 20 minutes per pound. They're going to be coefficients that really are very difficult to interpret because they're designed to go through this special formula in order to create a probability value. Okay, so let's have a look at what they look like. I'm going to open up a different data set here. I've got a data set here called, let's open data. Let's go to news channel for logistic regression. And I've got the special target field, which I'm trying to predict here, which is whether or not people subscribe to this news channel. You can see it's just two categories, no and yes, where yes is coded as 1 and no is coded as 0. You can imagine it as an app. Let's say it's a news app that people have to pay for or something like that. And we have some variables here which may impact upon that. How many hours they spend watching TV per day, and what their age is, and what their level of education is, and what their gender is. So if I want to run a logistic regression where I'm trying to predict this value out here, what it's going to do is it's going to give me a probability. And the probability is always going to be the probability of you being in the higher group, whatever the bigger group is. So even if these were coded as 1 and 2, it would internally change the coding to 0 and 1, and it would just pick, okay, whatever the higher value is, I'm going to assume you want to predict category 1 here, which means that, yes, they have the news channel. So the values we're going to get out of the coefficient table relate to the likelihood that these people are going to buy a news channel, subscribe to the news channel. So if I go to analyze this point and go down to regression, I'm now going to go to binary logistic. You can see the dialog box is kind of similar, except this time instead of independent and dependent, we have covariates, what it calls covariates. I'm going to pick up my dependent variable here, my target variable, accept news channel, yes or no. And you can see it here, no or yes. We're trying to predict the ones here. That's what it will predict by default. And I'm going to use age and years and just, again, using the enter method here, get it to produce some regression output for me. So this time, let me just hide some of this other stuff so so that we can see it more clearly. This time it starts off by saying, okay, here's your logistic regression output. Gives you some case summaries here saying you got one missing case out of 442 cases. And the internal coding I'm going to change, even though it already was coded to 1 and 0, says I'm just coding them as 1 and 0. That's what it does. So 1 represents yes and 0 represents no. And what it does is it starts off saying, look, if I just assume everybody is in the no group, because that's the larger group, then I would be 51% accurate overall. So that's just a convention it uses. It just says, okay, this is what your accuracy looks like without using the model, if you like, without using it. And then it gives us variables in the equation as we got before. Variables in the equation, except this time, the variable in the equation, the first one that shows is just a constant value, because this is a constant. And it's saying the constant isn't even statistically significant. And then it says, okay, variables that aren't in the equation at this point is age and years. It's the only one left. And it is statistically significant. So when we look below that, you see the stuff about blocks, because it assumes that you may be putting stuff in different blocks or using different models. Everything's just going in one block, and we've only got one variable here. It doesn't give me an R-square value. It actually gives me what are called pseudo R-square values, and they're usually pretty weak, even when the model's quite good. But suffice to say, think of this as 14.3%. The larger that value is, the Nagelkirch R-square or the Cox-and-Snell R-square, the stronger the correlation with the predictive value is. This is what's called a -2 log likelihood. This is a number that relates to the error in the model, and it's meaningless. It doesn't really mean anything to you. You're never going to look at it and go, wow, that's a really large number or a really small number. But it helps you compare one model to the next, because if I were to use a different variable and I just want to see how accurate the model was compared to the previous model, whichever one had the smaller -2 log likelihood is the better fit of the model. And then it shows me what the classification table is, what it was, how accurate it would be using a 50% cutoff value, a probability of 0.5, where if you're above 0.5, you're more likely to be in the yes group, and if you're less than 0.5, you're more likely to be in the no group. It tells me that just using age, I'd be 74.9% accurate in predicting the no's, by 75%, and I'd be about 54% accurate in predicting the yeses. And then finally, it gives me this equation in the table here. It gives me this constant where the B values do not mean that you get 0.5% probability increase in being in the news channel subscriber group for every year the older you are. Instead, these B values are refer to the log of the odds of being in that group. And that's a very difficult thing for people to get their heads around. But suffice to say, even thinking in terms of odds versus probability is quite tricky for a lot of people. Odds are not the same as probability. And thinking of the log of the odds is very difficult. And for that reason, we have what's called the exponentiated B value. You can see that these are both statistically significant. And these show that if they're positive numbers, it just means that the older you are, and both are positive numbers, the older you are, the more likely you are to be a subscriber to the news channel. It's saying for each year, you are 1.05 times slightly more likely to be a subscriber than not be a subscriber, because there's multiple ages and years. So that's really the only thing you can do when it comes to interpreting the coefficients, is really look at the exponentiated V values, look at the signs, and we'll see whether or not they're positive or negative, and look at the significance values. If I add in another variable at this stage, I can add in another variable. I'm going to add in gender. I'm actually going to use a category field this time. You can do this with binary category fields with linear regression as well. But if I go to categorical here and I say gender is a categorical field, you can see that it says, okay, I'm going to make everything with reference. The coefficient you're going to see is with reference to the first value. And the first value is male in here. If I click continue and OK, run that. Let's have a look. Let's go to the bottom. Now the accuracy's gone to 65%, 70% accurate on the no group, 59% accurate on the yes group. Now we have two values, and it's saying compared to the first gender group, you have a negative value. So who's compared to the first gender group? Females are compared to the first gender group. And it's saying that you are 0.47 times less likely to be a subscriber if you're female compared to male. These are known as odds ratios, which are used a lot in medicine. And age and years, very similar number to beforehand, 0.0578. So we could continue to do this and add in things like hours spent watching TV per day or something like that, or education level in years, and see if they make a difference. And again, we could use enter and forward and things like that. I'm just forcing them all in at this stage. And you can see that, yeah, that one of them's not significant at all. Hours spent watching TV per day is not statistically significant. Shouldn't be using that. Education level in years is, it's saying for each education level in years, you are 1.12 times more likely to be a subscriber than not be a subscriber. So these values here, if they're less than one, you're less likely to be a subscriber by that amount. And if they're more than one, then you're more likely to be the subscriber than that amount. Given that this only has two values, we get quite a big brutal change. But these are continuous variables, so it's a 1 unit change. So the exponentiated b values, the exponent b values are they're much more subtle for each unit. But if we were to see what this saved for us, what does this produce for us in terms of prediction? Well, like, you could ask for the probabilities and the group membership and click continue at that point and click OK. And it's saying, look, I think there's a 67% chance, that's a 0.67% chance that they're in the yes, that they are the yes group. And it's actually correct. I think there's a 21% chance they're in the yes group. So therefore I predict them to be no, and it's correct. And we can look down through it. Let's find one where it's got it wrong. Okay, it says, I think these guys, 81% chance they're in the yes group. So it predicts them to be yes, but it's wrong. It's a no. So when we look at the crosstab of one against the other, it's exactly what we saw earlier on when it was showing us the model fit statistics. It's just looking at the predicted group, which I'm going to put in columns against the actuals in the rows. And we could click on cells here and ask for row percentages and click continue and OK. And it says OK. Oh, sorry, wrong variable. Not gender, of course, but this variable. Click OK. It's saying, OK, look, 68% of the no's have been correctly predicted. 62% of the yeses have been correctly predicted. And overall, it's probably going to average out about 65% or something like that. So that's how one way in which we might assess how well the model fits. So it's a very different approach from linear regression because of this, the way in which we have to convert the coefficients into probabilities. And it means the coefficients have to be turned not into the raw scores, the raw values, but actually the log of the odds of you being in the key category outcome. And that's converted through a formula which happens to be 1/1 plus e to the power of minus z, where minus z is the equivalent of the coefficients, just for the record. Now, it turns out SPSS, as you can guess, has lots of regression methods available, especially if you have the regression models module added to it, which is where you'll find logistic regression that comes with the regression models module. Many additional methods, however, are made available through SPSS's integration with R and Python. So you'll still see a lot of free integrations, lots of other types of regression that one can do. Some additional resources. So we have some additional videos and resources around things like non-linear relationships and things like moderation analysis, mediation analysis, which is used a lot by students. You can also find out what versions of modules what modules you have installed. If you click here to this URL, take you to that and see exactly what's included in the regression model, and then some other materials which will link you URLs here, which will link you to choosing the correct statistical test or how to interpret statistical tests, and a link to our blog series on statistical testing and procedures. We have a number of different courses that are available. These are free to existing SPSS users. So if SPSS users are using these courses, SPSS users, if existing Smart Vision users can get free access to this. If you're not a Smart Vision customer, you can actually download them for a fee. And the last thing is that, of course, we provide a range of different consultancy services, including training, working on your data, working side by side your data, from 1 to 2 days to much more involved engagements. You can source your SPSS software directly from us. We can provide identification and recruitment of analytical skills in the organization if you're looking to recruit someone. We generally offer no strings attached technical and business advice related to all things analytical. And we have formal technical support services around the SPSS statistics product itself. I do hope you found that useful. We will have a series of other webinars coming up throughout the autumn and the winter. You might want to check out our website and register for them if you think that they might be useful to you. In the meantime, thanks very much for logging in, and we look forward to logging in again in the future. Thank you.